This video is intended to explain what exactly a computer is on a fundamental level. In the future, I will create another video that pivots off of this one to explain what programming is and how you can do it. To clarify, I will be using my desktop computer as a reference, but there are many other forms a computer can take. However, my goal is to instill very general foundational knowledge, so if I'm doing this right, you will hopefully understand how any computer would work. To begin, I should first clarify that whatever you are looking at this video on is not a computer. To be specific, it is a display that a computer is controlling, and I'm not just being pedantic. This distinction is important to understand exactly what a peripheral is. A computer peripheral is essentially any device that connects to and interacts with a computer. Your mouse, keyboard, and monitor are all peripherals. But to explain exactly how these peripherals communicate with the computer, I will first have to explain what a bit is. Basically, we use 10 digits when we count. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Whenever we go past 9, we just use the first two digits to represent it, 1 and 0. Is that you can do the exact same thing with an arbitrary number of digits. We could even just use those first comes 0, 1, and 0, then 1, and then 10. Afterwards is 11, and then 100. This concept is important because this means that you can count with anything that can be toggled between two states, even the powered and unpowered states of a wire. But keeping track of some numbers isn't all that useful. Computers are useful because they can do logic. For a moment, let's go back to considering on and off wires as actually on or off instead of using them to store numbers. A logic gate is basically a mechanism that inputs one or more of these on and off signals and outputs one or more on and off signals depending on the inputs. For example, the most simple logic gate is a NOT gate. The sole purpose of a NOT gate is just to invert whichever signal you send into it. So input on and it outputs off. Or if you turn off the input, it will output on. Another logic gate example would be an AND gate, which takes two inputs and has one output. An AND gate will output on if and only if both of its inputs are on as well. So if its first input is on, but its second input is off, then the AND gate will output off. But if the second input is also on, the AND gate will output on because both the first and second inputs are on. The simplest logic gate to physically make would be an OR gate, which outputs on if either or both of its inputs are on. So basically, it's the opposite of an AND gate. In fact, it quite literally is the opposite of an AND gate. If you just pass both the inputs and outputs of an AND gate through a NOT gate, it will behave the exact same as an OR gate. The reason why the OR gate is the simplest to physically make is because it's literally just two wires connected to each other. If either of the wires is powered, then the output will be powered as well. The reason why these logic gates are able to make computers useful is because, going back to considering wires as digits, you can perform basically any mathematical operation on these digits using nothing but logic gates. If you wanted to add 0 and 1, it would be equal to 1. In other words, you can add 0 to 1 by passing those wires through an OR gate. Except that if you added 1 and 1, the output would be 10, which is two digits, which substantially complicates the adder circuit, but the full solution is outside of the scope of this video, so we will be moving on. In conclusion, the computer treats everything as sets of on and off signals, which it can pass through to different logic circuits like the aforementioned adder. But that begs the question, how does it know which logic circuit to send which set of on and off signals? To explain this, we must first explain what RAM is. The RAM is essentially a large series of traps that temporarily stores whether a wire is on or off on command. The computer can then read these stored signals whenever it wants in the future. However, modern computers will only read the signals in large groups, typically groups of 8. Going back to the question of how the computer knows what logic circuit to send what signals to, essentially, the computer will read a set of 8 signals from the RAM, and it will treat the 8 signals as a single 8-bit number, and then it will execute whatever operation corresponds to that number. For example, maybe the computer has an operation to simply add together the next two values in the RAM, and that operation is represented by 000000000, aka operation number 0. When the computer runs, it will go through the values in the RAM one after the other. First it reads 000000000, so it knows to treat the next two values as numbers, which it should add together. Then it reads 000000001, and then 000000001 again. So it will feed those two values into an 8-bit adder, and the result, of course, will be 000000010, because 1 plus 1 in binary is 10. But where exactly would it place the number that is computed? To answer that question, we must answer what a register is. In case it wasn't yet clear, all of the different operations are built into the CPU, and along with them, the registers. Essentially, a register is like a single piece of RAM, a single set of 8 signals. The CPU has multiple registers which it uses during computations. For example, in a real CPU, there would be no add together the next two values in the RAM operation. Instead, there would be a place the next value of RAM into this register operation, and a separate add together the values of these two registers and store them into this third register operation. So to add together the next two values in the RAM, you would have a place the next value of the RAM into the first register operation, followed by a place the next value of RAM into the second register operation. And then a add together the values in the first register and the second register and place it into the third register operation. And naturally, there is also an operation for moving values in the registers back into the RAM. This is, in essence, what programming is. You write this series of operations that are loaded into the RAM. The CPU then reads those operations sequentially, and depending on what operation it reads, it will do something with a number somewhere. But wait, remember when I said that RAM only temporarily stores signals earlier? The reason I said that is because the values stored in the RAM actually disappear when the computer turns off. This is why your computer has a hard drive. The drive stores values permanently that can then be loaded into the RAM, and then the values in the RAM are loaded into the registers. But wait, if every single value in the RAM goes away when the computer turns off, then how will the first instruction to load the values on the drive into the RAM be executed? The CPU wouldn't be able to read the instruction to do so because it's not in the RAM. This is what the BIOS does. You may have heard this term before. It is essentially a hard-coded program built into your motherboard, which just force feeds some operations into the CPU so that it loads your OS into your RAM. And from there, your OS tells your CPU what to load next. Your OS is basically a program which loads other programs into the CPU and helps them run. This YouTube video is probably running in your browser, and your browser is a program which your OS loaded into your CPU. The OS also provides some other utilities, such as handling signals from peripherals like your mouse or keyboard and telling other programs whenever you click or type. And yes, we are finally discussing peripherals like we said we would 10 minutes ago. The OS also contains a program which decides what to display on your monitor, which it does by sending information to the GPU, which then sends it to your monitor. But to explain exactly what the GPU does, we will have to wait until the next video because I am tired. Goodbye.